really at the end of chapter 12. So welcome back to chapter 12. This will be our last coverage of it, and we stopped here on essentially moving platforms. We did an example last time with a rotating platform that rotated every second. These are examples now of smoother moving platforms that just slide to the left, to the right, or up and down, and they're pretty easy to code once you've gotten the runtime added and the inner frame listener attached to it. Then you have a function that will run 30 times a second in which you can put any code you want. So as an initial example, I just have a red platform that moves, kind of bounces back and forth across the screen. So here's the example. And again, these are all examples from the book's resources, the chapter resources. So this is in the chapter 12 folder, and it's just called Moving Platform. And you can see that there's a magic ball and there's a red rectangle. The red rectangle is the moving platform. Here's an example of it running. So the moving platform just moves left and right. This isn't a game by any means. It's just the moving platform. So how do we get a platform to move? The basic idea is that we need to, if we want the platform to move to the right, then we add some number to its x location. So in this example, the platform is object 1. That red rectangle is object 1. So when I want it moving to the right, I'm going to add a number to it, and that number is a number of pixels that it will shift to the right, or 30 times a second. So you don't want a big number. I normally start out with a 1 or a 2, and then just see if that gets me the speed that I want. You'll see in this example, I've actually not used a fixed number. Instead, I've used a variable. I call it platform speed. And if you peek in the code, it starts, I think it's set to 2. This is nice because the trickiest part of this is to know when to stop moving to the right and start moving to the left, or when to reverse direction. Likewise, moving to the left, we take a certain number of pixels off of the x location. So we subtract from the x location to move it to the left. And if we want the platform to stop at the very left edge of the screen, it's not actually x equals 0, because remember that the x is in the center of the red rectangle. So it's actually half the width over from 0. So the little bit of code example here is just hard-coded for object 1 to determine when it hits the right edge at 320 pixels over and when it hits the left edge at 0 pixels over. And when it hits one of those edges, it reverses direction. So I reverse direction just by negating the value of platform speed. So the code looks a little weird, but I think this ends up being maybe the most compact, easy to understand way to do it. Just when I hit a barrier, when I hit a place I want to reverse direction, I can just negate the value of the variable, with the minus operator here, and that'll switch directions. So if it was going to the right, it'll start going to the left. If it was going to the left, it'll start going to the right. That's a left and a right direction change. I have a second, more complex example called Move Everything. Okay, now I gotta find the folder again. Mobile Designs, Chapter Resources, Chapter 12, all the way down to 14. Here we go. All right, this is Everything Moves. So I just threw an example of lots of different things so that you can peek into the code and see how all of the different movements are achieved. But I've got rotating in each directions. I've got an elevator that moves up and down. I've got a platform that moves left to the right. I've got stacked rotating objects. The gear and the older black and white magic ball are kind of rotating as a single piece, and the gear itself reverses direction every so often, and the red rotating box just kind of clicks like a counter of some sort, stepwise. All of the code to do this is going to be found in inner frame. So just to peek at it, it's not a tremendous amount of code, but if you're trying to get something to work like any of these, you can peek in the inner frame snippet and see how I've achieved each of the effects. They all are based on the same principle of changing a value a small amount 30 times a second. The exact amounts are based on just some experimentation. And so I'm using platform speed and a second variable I've created called elevator speed. I hand code in some cases, like the magic ball is rotated at 7 pixels 30 times per second, which is why it's spinning kind of faster than everything. And since I don't have it reversing direction, I don't need to ever change 7 to +7. So it's just hard coded in. Anything that I need to reverse direction on, I use a variable to use this technique to negate the direction of movement, horizontal, vertical, or rotational, when it hits some sort of arbitrary limit that I want it to hit. That's chapter 12. You are now a master of physics. At your command are the key elements that cause and sustain motion in a 2D world. You are in control of gravity, mass, friction, bounce, and density. You know how to create objects of different shapes and add them to the physics engine and take control of the world that you have created. You also know how to add touch sensitivity to the entire screen using the runtime object, and you know how to create a game and tap into its 30 frames per second runtime so that you can animate stuff in addition to doing everything that you've learned to do with physics. So this is the end of chapter 12. It leaves you in a good spot to do lots of different fun stuff, but there's more. There's so much more to learn. So welcome to chapter 13, collisions. This is the next step after you've mastered all of the techniques from chapter 12. You know, sometimes I think it's confusing because people think, well, what? Wait a minute, you're going to show us how to create collisions? Haven't collisions already been occurring? Every time the magic ball hits something, isn't that a collision? Yes, it is absolutely a collision. But it's sort of like, taps might be occurring. Your user might be tapping on your screen, but does that necessarily mean you're doing anything in response to it? No, it doesn't. You have to listen for taps, and only when they do tap something that you're listening to, do you take action. So it's the same thing with collisions. For the most part, we don't, by default, care about the collisions. They will occur. They will occur realistically. The physics engines will do the calculations to make it look right on screen. But by default, we don't take any extra action additionally when the collision occurs. If we want to do that, then we hook the collision listener up to what we want to listen to. It is not tough to do at all. Once we have an image or a physics shape or the runtime, we can hit that add listener button and choose the collision listener from the list of listeners that are available. In and of itself, this tiny little code stack isn't going to do anything because the ball won't collide with anything, because there's nothing for it to collide to, and if there was something for it to collide with, we haven't created a physics world, so it's not going to collide with anything. But when you attach the collision listener, what I'm trying to show you is this is the additional chunk of code that will appear right above the object that you added the collision listener to. So if we want to give it something to collide with, like a ground rectangle, you would add it and then add it as a physics body, set it to be static as the ground so that it won't move. Okay, so I'll tell you what, I'm going to save my design first so that I have the project folder set up. So I'm going to need a new folder for chapter 13. I'm going to call it chapter 13, and then I'll call this design ball 1. All right, now when I find the image I want for the magic ball, say, here's the black and white one. We'll find the color one in just a second, and then I want a rectangle for the ground. Let's say make it look like a bit of grass. let's start up physics. So I'm heading over to physics. I'm going to set up physics. Then I'm going to select the magic ball and I'm going to say add body. And because we know that the default bounce is really low, I'm going to crank it up so we get a little more bouncing. I'm going to select the ground and hit add body. And then I'm going to change its physics body to static by hitting the button that says dynamic so that it changes to static. That's it. Let's save it. Let's head to the code, get it to run. You'll notice it's bouncing. Let me do it again. It's bouncing wildly badly off to the side. Doesn't make any physics sense. So, do you guys remember what's going on? We talked about this last time. If we have odd physics occurring, we want to switch to hybrid draw mode. Try it again. Again, this magic ball image is very, very jagged, very pixelated around the outside. So by default, drawing a code tells Corona to try to come up with a physics shape for the image using this automated technique. But the automated technique can't handle an outline that's that jagged or pixelated or anything remotely close to an outline that's that jagged or pixelated. So the fix is, for this image, this technique just doesn't work. So we're going to switch to use a circle, hit the refresh or resync button to size the physics body to match the circle. And now we'll get a ball that bounces. So we haven't added collisions yet. So the first choice you have when you want to add collisions is you ask yourself, well, what do I want to add the collision listener to? Do I want to listen to the ball or do I want to listen to the ground? There's not a wrong answer here. When the ball hits the ground, there's a collision, and when the ground hits the ball, there's a collision, and you would get essentially the same data either place. So it just depends sort of what your purpose is in adding the collision listener. What is it that you want to do? For the first simple example, it's just adding sound effects. So it really doesn't matter. Although if you had different sound effects, so the ball, when it hits different things, makes different sounds, then you might want to add the collision listener to those different things. Then again, it would matter whether there were other objects that are colliding that would make different sounds as well. And so the more complex it gets, the more you have to think about maybe what do I add the collision listener to. In these simple apps, it just does not matter. So I've selected the magic ball. I'm going to hit the add listener button on its details panel. Tap is the default, which we're not doing. I'm going to head down to collision and add collision. So this has added the two extra script objects that we talked about at the beginning. It's added the collision handler and the default collision support. So if we save it now, what we'll see is, as soon as I can get over to the simulator, is we're getting detailed information out of the console. It says object 1 colliding with object 2. Object 1 is the magic ball. Object 2 is the ground. If we had attached the collision listener to the ground, it would say object 2 is collided with object 1, but it's the same information. And then so to add a sound effect, to get this a little bit more interesting, we would load a sound. Mobile designs, how about chapter resources? What do we just get into? There we go. Low bump is one of the sounds. So I've added it. There's no sound because I haven't played the sound. So I'm going to hit play sound. There's only one sound. If I save it now, you're going to hear the sound, and it's going to play when the app starts. It plays when the app starts because it's in the main execution thread of the app. All of these script objects generate code that will be executed when the app starts, except for the code inside the collision handler. Because it's inside of a function, it will only run when the function's called. I don't want the sound to play a single time when the app starts. I want the sound to play every time a collision occurs. So that means I need to move object 9 play sound into the function object 1 collision handler. I do that by selecting the object in the stack, hitting the move play sound into function, and hitting OK since there's only one function. Now when I save it, we'll get what you're expecting, which is a ball that bounces and makes a bouncing sound, sort of basketball bouncing sound maybe when it hits the ground. That is the basic collision listener. So there's some syntax to learn or to be aware of. The syntax is in the default snippet, but the basic idea is you can ask Solr 2D, what did I collide with? Which is fairly common to want to know. You know what collided because you added the listener to what collided. So we added the listener to the ball. So we know when the ball hits something, object 1 is colliding with something. If we have multiple things for it to collide with, we don't necessarily know, well, what did I collide with? So we can ask it by using this syntax event.other. Event.other will give us access to the thing that we just hit. And if it has an ID, then you can ask for event.other.id. If it has a name, you could ask for event.other.name. And this is where if you had multiple things for the ball to collide with, so that there were more than one potential event.others, then you would use an if statement to parse that out. You could say if event.other.id double equals object 2, that's the ground, then we'll make the ground sound. Or if it hits something else, the ID would be different, and you could play a different sound. If you're coding this by hand, the event.other table isn't by itself all that helpful, because if you tried to look at event.other at the console directly, you get output like this, which doesn't make a ton of sense and isn't super helpful. You really don't want that. You want to have information about what you hit, at least saying the object ID. And even better, if you've named it, then we'd like to see it say, for instance, the ground. That's not an issue for Draw to Code users because obviously I code it to look for the ID or the name. I don't have it. Try to spit the table out to the console. But if you are coding by hand or tweaking a design by hand, just be aware that by itself, event.other, like any other table, is a container of information. And if you try to spit the whole container out to the console, you'll get this, memory address kind of output. All right, so the other thing to know is collisions do have phases. So there's two phases. There's began and ended. And we'll make use of these to do some stuff. I think the big example I have in this chapter is when the collision starts. For instance, when the magic ball starts to hit something, we're going to tint what it hits red to try to make it look like it's taking damage. And then when the collision ends, however many milliseconds later, we'll remove the red tint. So you'll get this flash of red when something is hit by taking advantage of these began and ended phases. We'll peek in the Draw to Code example here, but obviously we didn't talk about doing that. All I did was added the sound effect to the collision handler. And so the sound is playing twice. You can't really tell because they're played at essentially the exact same moment. But if it was something that we needed to be more careful about, we would use some if-then logic to figure out which phase we were in and then limit what we did to that particular phase. So it would be better in the example that I just showed you if I did put in some of that logic and I made sure only to play the sound once per collision instead of having it play twice. We're gonna code a little lap then, or take this to the next step, which is I'm gonna fix the issue with the phases, and I'm gonna add a counter to keep track of how many times the ball has bounced. I'm going to dive into it and do it, but again, if you already know what you're doing or want to try to get ahead of me, by all means do that. I'm back at our app. The reason that there were two rectangles in the stack is you just saw is because I added a second rectangle to try to make the ground look more like a side view of grass and dirt, soil. So let me add that just to be consistent with some sort of, that's pretty dark rich soil. There we go. So now when it runs, it'll look like the example in the keynote. I don't have to add the brown dirt to the physics engine. It's just there as something to change what the user sees. It's not part of the physics engine because the ball could never hit it. All right, so we want to add a counter. That's going to be a piece of text. To use a counter, I need to create something, right? If I want to count, I need a variable to store the count in, and it's an app variable, so it needs to be outside of any method. So I'm going to head to snippets, and I'm going to add a new snippet. I'm going to call it like I normally do, app variables. I only have one at the moment. Let me zoom in on that. I only have one at the moment. It's counting bounces, so I'm going to call it bounce counter. I'm going to put the app variables up top, and I'm going to hop into the collision handler. And I already have a snippet there. What you'll notice is I was smart enough in drawing the code to limit myself to a particular phase. If you don't want to limit yourself to a particular phase, you could just add code down here, which would execute both for began and ended. If I want to limit myself to began, I've also done another check, which is I want to make sure it did hit something valid. It hit something that exists, that still exists. And if it did, I also check to see whether it has a name or an ID. And if so, I spit that information out to the console. So let's add a name because I forgot to do that. So for the green grass, I'm going to call it ground. That'll give us slightly better information out of the console. And then back to the snippet. Let's just do our counting. So I want to say bounce count equals bounce count. Oh, it's going to be one of those days. Plus 1. And then I want to update the on-screen count. So that is, we can see it's object 11. You can hover over it. You can look at it in the stack. But I'll say object 11.text equals bounce count. All right, so when a collision occurs, it's going to count up, and it's going to update the on-screen counter with the new count. So let me save it. And oh, I've done something wrong. It's the trouble trying to talk and code. Absolutely. By itself, listing an identifier isn't a valid statement. So good catch. All right, I've done something else. This is it's just going to be one of these days, I think. Great catch. There we go. Let me make it a little bouncier so that you can get maybe a better sense of what's going on. So I'm heading back to the ball, object 4, and crank that bounce up a little more. That'll give us a few more bounces to watch. But what you might see is it seems to be counting by 2, right? And then it ends on an odd number, which is weird if we're counting, by evens. Why does it end on an odd number? It initially might seem a little bit weird. I think you already know, but what's going on is every time the ball collides, there are 2 phases, began and ended. So every time the ball hits, this object 1 collision handler is called twice. That means for every bounce, assuming the ball comes back up off the ground, for every bounce you'll get 2 counts because this code runs twice. It runs twice because I did not put it in here with the other code that is phase limited to one of the phases. Why does it end on an odd number? Generally it's going to end on an odd number because that last bounce, it didn't lift off the ground. The last bounce settled the ball on the ground, so there was no ended phase. Okay, but now let's fix the counter. If you're already ahead of me, you probably have already moved this code into the location where it needs to be. I'm going to put it right in here. I'm going to copy this line. I'm going to cut and paste this bounce counter counting up to here and indent it correctly so it's all lined up. But this one change will change what we get. So now you see we're getting correct counting out of the magic ball. let's do two more little fixes that we should be doing. So I'm going to add a name to the magic ball. I'm going to call it the magic ball. This is the black and white version, which is obviously less magical. We'll use the color version in the next example. And then I do not want the play sound playing twice. I mean, assuming the game is more complex and there's lots of sound effects going on, that's taking up two channels, two of my 32 channels for the sound effects. So it's wasteful. And although in this simple app, it doesn't matter, when your app starts to get slightly more complex, it may end up mattering. So I'm selecting play sound, and I'm going to pull down the edit menu and say copy the script objects code to the clipboard. Also going to remove it from the generated code by unchecking this checkbox. I'm going to head back to the snippet which we're editing, and I'm going to paste the sound code right here so that it is inside of this logic that limits my response to collisions to a particular phase. That should do everything. Okay, so we can add the collision listener to the runtime. So we don't have to add it to, say, the ball or the ground or a particular physics body. We can add it to the whole app. I'm not going to do it right now because there's a couple of changes I want to talk about before we look at it. When you add the collision listener to the runtime, any two physics bodies that collide will report that collision to that collision handler. So everything that collides will be reported. You'll get a lot more information out to the console. And the syntax for figuring out what collided with what is different. If you added the collision listener to a particular object like object 1, then you know when it hits something, object 1 has hit something. When you add the collision listener to the runtime, you don't know the identity of either of the two objects that collided. You know that two physics bodies collided, but you don't know if it was the ball and the ground or the other ball and the ramp or the ramp and the lockbox. You have no idea. So for that reason, the syntax for working with the runtime collision handler is different. The names of the two objects that collide are event object 1 and event object 2. Object 1 and object 2. So in the collision handler for the runtime, there is no event.other. So it's a really common mistake to get used to using the syntax event.other, and then you might paste some code into the runtime collision handler, and it contains an event.other, and that'll cause an error when you try to, when the collision first occurs, you'll get an error. So instead, it's the syntax event object 1 and event object 2. There are still multiple phases, 2 phases, so you still want to limit yourself to a particular phase if it makes sense to. So the snippet in Drawing a Code still does this careful check to make sure we're in a particular phase and neither of the objects are nil. And if the ID exists, then it'll display the ID of both objects. The output you get to the console will be different. So the next example essentially has a stack of the lockboxes. It's the stack of lockboxes we had last time, the steel ramp or the iron ramp, and now an upgraded color magic ball. And so I've got 2 examples in the resource downloads. One is the collision listener was added to the magic ball, in which case you should get output along the lines of the magic ball hit the ramp, the magic ball hit lockbox 5. The lockboxes are given numbers so that you can tell them apart in these examples. But you'll see in this top example, when you're listening to the ball, you get this ball-centric report at the console. The ball hit all these different things. That's not at all what you get now if you listen to the runtime. If you add the collision listener to the runtime, you get this report from any 2 things that collided. And so you'll see stuff like lockbox 6 hit the ground. What does that mean? Well, when you watch the app running, this is lockbox 6. it was the first thing to touch the ground. You'll see when I run it that it hits the ground first. Therefore, it makes sense that that's the first reported collision. And actually, as you work your way get down, it'll actually make sense. The lockbox 5 will hit lockbox 6. 4 will hit 5. 3 will hit 4. If there's bouncing going on in the iron boxes, the lock boxes, then you'll get each of those bounces as collisions. You can see here when the ramp hit the ground, when the magic ball hit the ramp. That was reported from the ramp's perspective. So you get this really detailed report of all the collisions that occurred when you use runtime. If that's what you want, if that's what you need, then that's awesome. If it's not, then it may be giving you way more information than you want. All right, this is Collisions 1 runtime. It's set up essentially the same way as the version we did last time. There's a timer with 6 repetitions that creates 6 of these lock boxes. So you'll see them created from this starting point and then dropping and stacking up. The physics settings, the bounce and friction, everything have been set so that the lock boxes will stack up fine. The ramp gets rotated and then dropped, and then the magic ball here is created and dropped. There's only one ball in this example. And then here's the runtime, and here's the collision handler for the runtime. Here's the snippet that we were just looking at in slightly more detail in Drawn to Code. So let's run it. There's no sound effects. There's nothing going on except the drop. And it's a tough thing to do because it happens fairly quickly. So I'm going to slow it down because, again, we're in control. So I'm going to head to physics and I'm going to decrease gravity just to give you a fighting chance of watching what happens on screen and also the console. It's still tough, isn't it? The crates are spawning a little too quickly, so they're forcing the physics engine to shove them apart if you watch. And each of those creates collisions, which are a little messy. So we could work on this a little bit to clean up the console output, but the bottom line is you're getting this huge dump of collision information that may be way more than you want or need. If really all you care about is the magic ball hitting something, then you probably don't want to add the listener to the runtime. But if you care about more stuff, if you want to make sounds, for instance, as these crates stack up, if they were to get their own slightly more metallic thump sound, then this might be the way to do it. Or if anything hitting the ground gets a slightly different thump than a metallic thump, or the metallic objects hitting the ground will make a different thump than the magic ball if it hits the ground. If you're trying to be that careful, that creative with your app, then this information potentially becomes essential. So this is simply a table from the book with a summary of the 2 different approaches. So 2 different ways to do it, although conceptually you're doing the same thing. You're paying attention. You're telling Solr 2D, I want to pay attention to the collisions so that I can take some action when a collision occurs. That concludes what I have time to get to today. We will continue coverage of Physics 2 collisions, and we will work to make what we do in response to the collision more and more sophisticated. So we will be tinting the crates when the magic ball hits them. And then our ultimate goal in this chapter is actually to inflict some damage. So we want the magic ball, when it hits the crate, to impart some damage that is realistic given the physics engine's calculations. So we're going to add both a damage bar and a health bar, if you look ahead in the chapter, to the lock boxes. And when the magic ball hits them, we will impart some damage and we will take away from the health bar. It's the exact same thing, except the bars move in different directions. So that's where we're heading, and we will head there.